This is the first lesson in the Computer Security Operations Center, or CSOC, training course. Throughout this course, we will often just refer to the CSOC as a SOC. The purpose of this lesson, then, is to review some basic networking principles and protocols and to introduce some basic SOC concepts.
In this module, we will cover the following topics. First, we will review common network protocols and devices. Second, we will introduce the common terms and names you will encounter in discussions of a SOC. Third, we will introduce the three elements of a SOC, namely people, processes, and technology. Fourth, we will look at where SOCs fit into the common NICE framework often discussed in the field. Additionally, we will have a quick knowledge check at the end of each lesson so you can see how well you are understanding the items presented. Finally, we will also provide a list of references and resources that you can check for additional information on SOCs, though we will not spend any time on them. The first topic to cover is a review of networking. This portion of the lesson is not designed to be a course on networks, but is instead designed to be a refresher on a number of networking topics which you will need to understand when learning about SOCs. If you have not had a course on networking, you may want to take some time to further explore the topic utilizing sources you can find on the internet. The topics we will cover include those displayed here. This is a lot of material that we will cover in a short period of time. You may find it helpful to stop the video and back up if there is a topic that you did not understand. Again, you may decide to explore the topic in greater detail on the internet. Our first topic is encapsulation. Encapsulation is often compared to an envelope in which you insert a letter and on which you write an address before slipping it into a mailbox. What is important to the post office is not the contents of the letter. In fact, the post office will not even look at this. They are interested in the address you have written on the envelope and how best to ensure that it gets to its intended destination. This analogy can be further expanded if the address or contents of the envelope contains additional routing information. The post office may deliver it to your address, but then somebody else has to make sure that it gets to its intended recipient. The post office does its job of delivering it to your organization, where another person is tasked with getting it to the right office or individual. Encapsulation in networking works in a similar manner, where we have packets of information that have been formed on one computer, which are then sent to other systems. At the lowest layer, the network is responsible for making sure the packet gets to the right system. Once there are other protocols that are responsible for ensuring that it is processed by the right software or application so that it is received by the intended recipient. Let's take a look at how this might work by looking at one layer in a network and how encapsulation occurs. In this example, we have the data which could represent the letter in our post office example. We want to slip this into an envelope on which we have to provide instructions on where this is to go. We add a header to this data, and in some cases possibly a footer, which are designed to tell what to do with this data, and then we bundle these together. This can then be passed as a single entity to the next lower layer, which will handle this entire bundle as the data which it will then also add a header and possibly a footer to. When a system receives information from another system, the process is reversed, with a layer receiving information from the layer beneath it, which it then strips off the header and footer from in order to determine where to send it in the layer above. This encapsulation process is utilized in the Open Systems Interconnection Model, or OSI model, that is taught in introductory networking courses. The OSI model describes how to package data at the different layers in the model. Each layer only sends information to the layer directly below it when it is sending information to another system on the internet, or directly above it when it has received information from another system. There are potentially multiple protocols and services at each layer of the model, so at any given layer, it must be determined where to send the information once it has been unpacked. This is where the header and footer come into play, so the layer knows what to do with the information. Here's a depiction of the 7 layers defined in the OSI model. The top 3 layers of this model cover the application being used on the computer system and various things done to the data. The next 3 layers are concerned with the transportation of the data through the network and to the destination system. The bottom layer covers the actual physical transmission media. Individually, the layers accomplish the following tasks. The application layer is used by end-user software such as web browsers and email. It allows software to send and receive information and present data to users. The presentation layer prepares data for the application layer, the layer just above it, as was discussed in the encapsulation discussion. It covers how to encode, encrypt, and compress data. The session layer creates communication sessions between devices. It is responsible for maintaining the connections between systems. The transport layer takes data transferred from the session layer above it and breaks it into segments on the transmitting end to pass to the next lower layer. It is also responsible for assembling the segments on the receiving end when it is passed data from the network layer. The network layer is responsible for breaking things into network packets and reassembling the packets on the other end of the transmission. It is also responsible for routing packets through the network. The data link layer establishes and terminates a connection between 2 nodes on a network. It breaks up packets into frames on the transmission end and assembles them again on the receiving end. Finally, the physical layer is responsible for the connection between network nodes using something like a physical cable or through wireless transmissions. The OSI model has been used for years to describe how networking can occur and to describe the process of encapsulation. It, however, is not really used in the real world. Instead, the majority of networks on the internet use the Transmission Control Protocol / Internet Protocol, or the TCP/IP protocol suite. This model has only 5 layers, and some show it as only 4, as opposed to the 7 layers in the OSI model. It does, however, implement the encapsulation process as was discussed, though it doesn't always stick to a strict following of the only communicating with 1 layer above and 1 layer below rule. Overall, the OSI and TCP/IP protocols have much in common in practice. The TCP/IP protocol suite consists of a number of different protocols seen throughout the 4 layers of the model as shown here. In this diagram, the lower 3 layers correlate with the lower layers of the OSI model very closely. The top 3 layers of the OSI model all fit into the application layer of the TCP/IP protocol suite. For the most part, the protocols shown here and those not shown here follow the encapsulation concept and communicate only with the layer directly above it and below it. The ICMP, or Internet Control Message Protocol, embeds its header inside of an IP packet, for example, and the complete packet is then handled as an IP packet when sent across the internet. ICMP is considered a support protocol and is not used to transport data between systems and end users. At the application layer, the protocols are found that handle common applications users utilize. These include the Hypertext Transfer Protocol, which we all know as HTTP, and which handles our web traffic, and SMPT, or the Simple Mail Transfer Protocol, used for sending and receiving emails. At the transport layer, we have two workhorses of the TCP/IP protocol suite. The first is the Transmission Control Protocol, or TCP, which is a connection-oriented protocol, and the other is the User Datagram Protocol, or UDP, which is a connectionless protocol used for loss-tolerating and low-latency applications. At the Internet layer, we can find ICMP, which we already mentioned, and IP, which is the Internet Protocol. This is another workhorse protocol in the TCP/IP protocol suite. It is important for sending datagrams across the Internet. The link layer is the lowest layer in the TCP/IP suite of protocols. It is here we find a number of protocols used to connect between adjacent nodes in a network segment. This diagram depicts what occurs when sending a packet across the Internet. Notice at the top two layers, the transmission can be considered between the two endpoints. At these layers, the protocols are not responsible for the routing of the packets through the many systems that make up the Internet. They are only concerned with the two endpoints. At the bottom two layers shown here, the object is to route the packets to their correct destination. Routing decisions are made as to where to send the packets for the next leg of the journey. This may include through LANs, as indicated here, as well as across wide area networks, probably several of these before getting to the local network connected to the destination system. At the destination endpoint, the packet is received and the system has to decide how to handle it. It will look at the headers to decide where it needs to go at the network layer. This might include being handled by the ARP, or Address Resolution Protocol, which helps to determine the correct media access control address or the network given a specific IP address. It could also mean being handled by the IP protocol, which will determine if the IP address of the destination matches this system's IP address. It then needs to determine where to send it at the transport layer. This might mean being handled by TCP, the connection-oriented protocol, or UDP, which is connectionless protocol. Or it could be handled by ICMP, which we mentioned before, can also be viewed as being at the same level as the IP protocol. If it was shuffled through TCP, it could then go to one of several services such as HTTP, SMTP, or FTP, the file transfer protocol. If it was shuffled through UDP, it might then be handled by SNMP, the Simple Network Management Protocol, or DHCP, the Dynamic Host Configuration Protocol, or by DNS, the Domain Name System. Finally, if ICMP was handling it, then it might then be handled by ping or by traceroute. What we are most familiar with on the Internet is to be able to gain access to a website by using its name, such as somesite.com. These names are used because they are easy for humans to utilize, but what the network uses is IP addresses that is included in the IP protocol, where the source IP address is placed to show where the packet is coming from, and the destination IP address, which is placed to indicate where it is to be sent. One layer above this, we see a source and destination port, which specifies what application or service that was the source and what application or service is the destination. The IP address is contained in a 32-bit location and is normally written as 4 decimal numbers such as 129.105.120.47. Each of these dotted decimal numbers is determined by splitting the 32-bit address into 4 8-bit parts, each represented by its decimal equivalent. Keeping track of what name is associated with its actual IP address is accomplished using the Domain Name System, or DNS, and will be discussed later. The Internet does not just consist of a bunch of systems which have had an address assigned to them in a haphazard manner. Instead, the address space is split into 4 network classes labeled Class A through Class D. An organization may be assigned an address space in one of these classes, which will give them a specific number of addresses they can then use to assign to their own systems. For example, a Class A network address will use the first 8 bits as its network address, and the remaining 24 bits will be used to specify a particular host. There are only 127 Class A networks, each of which can have over 16.7 million hosts. Compare this with the Class C network, of which there are over 2 million networks, each with 254 hosts. There have been several versions of the Internet Protocol. Remember that IP handles the source and destination address. When the format for the protocol was first created, enough bits were allocated for these addresses to handle over 4 billion Internet addresses. Unfortunately, since that time, the Internet has exploded in size, and it became obvious that unless something was done, the Internet would run out of addresses before too long. One method devised to address this was network address translation, which we will talk about more in a little bit. Another approach to handle the situation was to expand the size of the address space, which is exactly what was done in IP version 6, or IPv6. The address in this version expanded the address space from 32 to 128 bits. This results in a much larger number of possible addresses, more than 3.4 times 10 to the 38th, in fact. IPv6 also had some enhanced security features. When we as humans want to access a website, we type into our chosen browser the name of the website, such as whitehouse.gov, microsoft.com, nintendo.com, or the three names listed on the slide. Recalling our discussion of the TCP/IP protocol suite and the IP protocol in particular, the names we remember our sites by are not what the protocol needs. It requires a specific IP address for the site. The question then is, how does the name the human used get translated to the IP address the network wants? The answer to this is the Domain Name Service, or DNS. DNS will determine the IP address for a given web domain name. This translation from a name to a number is akin to the use of the telephone book, where we have an individual's name and we want to find their telephone number so we can call them. Because of the similarity of the two, DNS is sometimes referred to as the phone book for the Internet. Here's a diagram of how the DNS address translation process works. The first step is for the client to check with the DNS resolver. If the site has been viewed before, then the address could still be in the cache for the resolver and can be supplied quickly. If, however, the name is not in the cache, it has to ask somebody else for some help. The recursive resolver acts as a middleman between a client and a DNS name server. In this case, looking for the medium.com IP address. Next, a request to a root name server is made. This is followed by another request to a top-level domain server, and then a final request to an authoritative name server. The authoritative name server responds with the requested IP address, which is then sent to the client. Previously, we mentioned TCP and UDP. Let's take a look at them in a little more detail. TCP is a transmission control protocol. UDP is the user datagram protocol. TCP is connection-oriented, which is what enables a guaranteed delivery of packets. A connection needs to be set up before transmission begins. This is what makes the transmission slower, but will also mean that lost packets will be retransmitted. Earlier, we also mentioned that UDP was connectionless. This means that it is going to be faster than TCP, but that it also does not guarantee delivery. Because of this, lost packets will not be transmitted. All of this makes UDP a simpler protocol. In general, UDP is used for services such as video teleconferencing, where a lost packet will not have a large impact. TCP is used for services such as email, web traffic, and file transfers, where ensuring you do receive all packets is more important. We previously referred to the TCP protocol as a connection-oriented protocol. This differs from UDP, which is connectionless, and is sometimes referred to as a fire and forget protocol. This means that when UDP sends a packet, it is not worried about whether it was received by the destination correctly. The packet is simply sent and forgotten. TCP, on the other hand, has processes to ensure that packets are received and then reassembled in the correct order without losing any. To set up the connection between two systems, TCP first uses what is known as the TCP three-way handshake. The TCP three-way handshake starts the connection between two systems. It sets up several sequence numbers that will be used during the transmission to ensure packets are received in the correct order. It does this with a series of synchronizations, or SYN, packets, and acknowledgements, or ACK packets. The entire process works as follows. The system wanting to set up the connection sends a SYN packet and includes a number it selects to start the sequence. The receiving system sends back a SYN ACK packet with the initial sequence number incremented by 1 and a new synchronization number for the second system. The initial system then responds with a final ACK with a second sequence number incremented by 1. In essence, what has occurred is the first system tells the second, "Hey, I want to talk to you." The second says, "Okay, I'm ready, let's talk." The first system then says, "Wonderful, we can now begin," and the communication can commence. A couple of final comments. When the communication is to be closed, the systems exchange a pair of FIN and ACK packets to say, "I'm finished." Additionally, there is a limited number of TCP connections that can occur at any given time. This becomes important in a specific type of attack known as SYN flooding. To give you an idea of the type of attacks that have occurred in cybersecurity, we're going to take a look at a very famous attack known as SYN flooding. Successful attacks on computer systems often are the result of an undiscovered error in coding. They can also be a result of somebody abusing an application or protocol and using them in a way they were not intended. This is the case with SYN flooding. We just explained the TCP three-way handshake and how it works. The first system sends a SYN packet, the second responds with a SYN ACK, and the first then responds with a SYN packet again. That is how it is supposed to work. But what would happen if the first system sent a SYN packet but never responded to the SYN ACK? Or, better yet, what if the first system sent a SYN packet but spoofed another system's address in the source field or inserted an address for a system that doesn't exist? The second system is going to send the SYN ACK and wait for the ACK that will complete the handshake. But if no ACK comes, it will just keep on waiting. Now, if the attacker sends enough spoofed SYN packets, it can lock up the target system and not allow anybody else to communicate with it because there is a finite number of connections that the system can handle. you have effectively conducted a denial of service attack on the second system. In actuality, there is a timeout associated with the handshake, and the system will not wait forever for the final act. It will drop it when the timeout period expires. All the attacker has to do, however, is to keep sending packets faster than the timeout period in order to keep the system tied up. Let's take a final look at a comparison between OSI and TCP/IP. Let's first compare them in terms of their connection orientation. In the OSI model, the only transmission at the transport layer is connection oriented. In TCP/IP, as we discussed previously, connections can be connectionless as they are in UDP and connection oriented as they are with TCP. Next, in models of TCP/IP, we will frequently see the data link layer and the physical layers, which are separate in the OSI model, combined into one layer. There are some discussions of TCP/IP where they do separate these, however. Finally, in TCP/IP, the top three layers of the OSI model are combined into one layer, the application layer, in TCP/IP. When we talk about network devices, we generally are referring to networking hardware, which are physical devices connected to our network and are needed for a variety of purposes to ensure communication on the network. As a network or security administrator, you will come across a number of these, and you need to know their purpose and what they do. These devices can include hubs, which connect multiple devices on the network. They can also act as a repeater. A hub is the simplest network connection device as they don't conduct any filtering or addressing operations. Switches are generally a bit more intelligent than hubs. They also allow for multiple devices to be connected, and they provide a limited routing capability by sending packets to their destination. Routers are more complicated devices used to send traffic to its intended destination. They are generally part of an interconnected network path along which packets are sent. They can be configured with some basic packet filtering functions. Bridges connect two or more networks or network segments together. You won't see these devices as much as you would have in the past because more intelligent switches have taken their place. Gateways generally work at a higher layer of the model. Gateways provide translation between different types of networking technologies and protocols. The term modem, heard frequently, stands for modulator-demodulator. They are used to transmit network signals between different media, translating analog transmission to digital signals and back again. Repeaters are simply devices used on a network to amplify the signal being transmitted over long distances. Finally, access points, which technically can be used for wired connections, are more often heard in relationship to wireless connections. As their name implies, they are devices that allow access to a network. They are often seen in homes and businesses where they create their own wireless local area network. Just as administrators need to know about network devices, they also need to know about network security devices. In this case, these devices have a tendency to change a bit more often than standard network devices with new tools being introduced periodically. Network security devices are hardware devices connected to a network to perform some security-related function. This can also include standard computer systems that are running specific software to turn them into network security devices. The list of network security devices includes firewalls. Firewalls are designed to filter traffic to protect networks from harmful traffic that exists outside of the organization's network. There are a number of different types of firewalls, including packet filtering, stateful packet filtering, application or proxy, web application,
and next-generation firewalls. Intrusion detection and prevention systems are designed to detect and possibly protect against intrusive activity that is occurring on a network. They also can come in different forms with different techniques used to accomplish their goals. One way to categorize them is to look at host-based devices versus network-based devices. The difference between intrusion detection and intrusion prevention goes beyond detection versus prevention. Detection devices can be passive devices, just listening to a network, while prevention devices need to be inline in order to block or prevent attacks. Unified Threat Management, or UTM devices, which now are also associated with next-generation firewalls, were originally designed to be a single security device that provided multiple different security functions. They were designed to replace the number of different point products, each of which provided a single capability. A related device is a Security Information and Event Management System, SIEM, or SIM. These devices are designed to take the inputs from other devices and present them in a format to help administrators. UTMs not only present information, but can generate it as well. Network Address Translation, or NAT, or NAT, devices are used to map multiple local addresses to a single public one. This was at first important because we were running out of internet addresses in IP version 4, but it also serves to hide details about the internal structure of a network, which adds to the security. The NAT function often takes place inside another security device, such as a firewall. Filters, such as web and spam filters, are designed to detect and block malicious web traffic and unsolicited bulk email. Proxy servers are designed to sit between users and the internet with all traffic filtering through them. The specific traffic depends on the type of proxy server it is, which means the application it is designed for. Examples could be email and web traffic filters. Malware protection devices are similar to the filters mentioned before, as they are designed to filter malicious traffic, in this case specifically malware. This ends Lesson 1 of Module 1. It's time to do a knowledge check. What is the name for the process in networking where a lower layer protocol receives data given to it from a higher layer protocol, which is then placed inside of the lower layer's data? Framing, encapsulation, embedding, or encoding? The answer to this question is encapsulation. A Class A IP address would use which of the following subnet network masks? 1.0.0.0, 255.0.0.0, 255.255.0.0, or 255.255.255.0. The answer to this is 255.0.0.0. In TCP and UDP, what are the source and destination port numbers used for? They tell the network where to send the packets to, in other words, where to route the packet and where the packet came from. They limit the number of packets that can be sent to a system from a specific source. They are used to reassemble a message in the correct order at the receiving system, or they identify the process or service on the source machine and the destination machine that the message came from and is being sent to. The answer to this is they identify the process or service on the source machine and the destination machine that the message came from and is being sent to. Which network device is designed to provide translation between different types of networking technologies and protocols?
gateway, switch, repeater, or hub? The answer is gateway. If you answered any of the questions incorrectly, you may want to review the material again before proceeding. This concludes Lesson 1 of Module 1.